Einstein's bet, and the fine print we ignored. To see why C sits in the crosshairs, go to a Zurich patent clerk in 1905 staring at clocks that don't agree. Einstein's bet was simple and ruthless. Make the speed of light the same for everyone, everywhere, no matter how they move. From that axiom, space and time aren't separate rooms. They share a hallway. Length contracts, time dilates, simultaneity dissolves. The math follows, but the heartbeat is C, fixed, invariant, not a property of light alone, but the speed limit built into spacetime. That wasn't a guess. It was a decision to protect the laws of physics from the messiness of motion. If observers could disagree about C, Maxwell's equations would splinter by frame. So Einstein locked C into the geometry. You change C, you don't just nudge a number, you stretch the hallway. Clocks tick differently. Light cones tilt. Causality, which rides inside those cones, gets rerouted. And modern life banks on that bet every second. A navigation satellite skims Earth, firing timing signals that hit your phone within billionths of a second. The system works because engineers strip out relativity's distortions using a C that never flinches. A 30-nanosecond slip turns into meters of error on the ground. Millions of dollars ride on the assumption that the constant in the code is the constant in nature. Nobody at the control room is philosophizing. They just need C to be trustworthy. But here's the fine print most of us never read. Constants aren't museum pieces we measured once and framed. They live inside a web of conventions and units. We define the meter by C. We use atomic transitions to define the second. When we measure C now, we're checking the self-consistency of those definitions and the laws we've plugged them into. There's feedback in that loop. Models set priors that set calibrations that feed models. It's not corruption. It's how coherent science gets done. But it hides a subtle point. What's constant locally isn't automatically constant cosmologically. Physicists know this, which is why some kept a private folder with VSL. Do not send to referee 2 on the tab. The fear wasn't just reputational. If you allow C to vary in time or with cosmic conditions, you risk breaking cherished symmetries. Lorentz invariance, the idea that physics looks the same to any inertial observer, hangs on the constancy of C locally. Mess with that and particle physics starts to creak. Dispersion shows up where none is allowed. Thresholds for high-energy reactions shift. The standard model doesn't like surprises, and audiences don't forgive hand-waving. So every claim here gets a test, or it doesn't make the cut. Einstein also tied C to simultaneity. If the speed limit changes, the slice of now you can carve through the universe moves. Horizons, the boundaries past which events can't talk, depend on C and the expansion rate together. Raise C early, and distant patches share information faster. Some of the horizon problem melts. Lower it, and the universe fractures into islands that never exchanged a whisper. The map of what could have touched what is written with C as ink. There's another layer people forget. The theory side is full of guardrails. Energy and momentum need to be conserved. Stress energy must tell spacetime how to curve, and spacetime must tell stress energy how to move. If C varies, which equations keep their form? Do you break Lorentz symmetry explicitly, or do you keep local invariance and let C drift only with cosmological time? Bimetric models try to keep two speeds, one for gravity, one for matter, trading simplicity for survival. It's not arbitrary. Every choice throws a different punch at the data. Meanwhile, the practical world keeps reminding us what's at stake. Picture a satellite engineer who's been on shift for 12 hours, watching timing residuals wiggle within design spec. There's no romance in that screen, just columns of nanoseconds that must behave. A firmware update rolls out. A 30-nanosecond discrepancy appears and vanishes with a ground station handover. The fix assumes C is exactly the coded value. It works. The satellites don't care about cosmology. The network enforces local invariance with brutal precision. But local is the keyword. General relativity already shows us apparent variations. Light slows in a medium. Paths bend in gravity, coordinate speeds change in curved spacetime. None of that violates local invariance. Every free-falling observer still measures C as CVSL proposals target something else, that the limiting speed which sets those local light cones may have been different under early universe conditions. If so, the constant is contextual, not counterfeit. That's where the discomfort lives. We built a century of physics on an invariant C because it gave us a clean, universal scaffolding. Break that assumption and all the derived conveniences, synchronized clocks, invariant laws across frames, clean causality, need re-auditing. The pushback is justified. It forces any VSL idea to be specific about when, where, and how C moves without wrecking the laboratory world that keeps working. Some physicists pushed anyway. They argued that inflation solved old problems by adding fields and epochs. VSL tries to shift the load onto a changing speed limit with fewer knobs. The gamble is audacious. Trade mathematical elegance for a harder prediction about the world. That takes nerve and it costs. Whispered jokes follow talks. Grant panels ask if you're reliable. Private folders stay private. But seeds don't sprout in folders. A few heretics wrote the papers, sent them to hostile journals, and waited. They wanted a fight in the open, not in the hallway, and they got one. The heretics of variable C, VSL's rough birth. They knew exactly what they were risking. John Moffat typed the last line of a paper in 1992 and braced for the replies. His pitch was disarmingly direct. Let the speed limit run hot in the early universe, and the far sides of the sky could have talked before the light froze into the microwave background we see today. No extra inflattened fields, no carefully tuned plateaus, just a different rule then returning to the one we trust now. He mailed it out. Friends warned him. He sent it anyway. In the late 1990s, in a corridor at Imperial, Joe Magueijo and Andreas Albrecht hashed through a similar idea. Same wound, the horizon and flatness problems, and the same audacity. If C was larger back then, causal patches ballooned without superluminal magic. The razor cut differently, changed the limit itself, rather than stretch space faster than it. The math wasn't a slogan. It needed a prescription for how CT slides, how the Friedman equations inherit that slide, where energy goes when the constant moves. They wrote it down, invited the beating, and took it. Here's the hallway microclimate people remember. After a seminar, two clusters formed. One circled the speaker with questions about stress energy conservation, Lorentz braking, and whether the mechanism could be natural. The other drifted to the coffee, speaking softly about employability. Interesting was code for don't touch. Within a day, a senior voice muttered the phrase that locks doors. This isn't serious physics. A student standing nearby folded a printout and slid it into a drawer. Why that reaction? Inflation on the narrative. It reconciled the same puzzles with an elegant patch, a field, a potential, a period of accelerated expansion that ironed the wrinkles flat and stretched quantum seeds into structures. It was calculable, fertile, and crucially predictive. Nearly scale-invariant perturbations, Gaussian statistics, tiny non-Gaussianities. VSL, by contrast, looked like a blunt rewrite. Elegance makes friends. Bluntness doesn't. But the heretics had a case. Inflation added knobs. You could choose potentials, reheating details, couplings, enough room to park taste, and sometimes retrofit results. VSL tried to shift the burden away from an extra field to the kinematics of spacetime itself. Fewer knobs, bigger leap. In some models you break Lorentz symmetry explicitly. In others you separate sectors, giving gravity and matter different metrics so signals travel at different speeds at different times. It's not a free-for-all. Each choice leaves fingerprints on particle thresholds, on photon time of flight, on how perturbations freeze. In print, the stakes sharpen. To solve the horizon problem with VSL, the causal cone must widen early, then settle to today's value before nucleosynthesis and structure formation tighten constraints. Push C high enough, and the universe's far corners can exchange information. Relax it in time, and you don't wreck the synthesis of helium and deuterium. Flatten the universe without invoking an inflationary epoch, only if the altered dynamics act like a temporary antidote to curvature's growth. The equations become unforgiving. If energy isn't conserved in the naive form, you need a modified continuity equation. If Lorentz symmetry bends, you must say how experiments miss it now. A postdoc remembers the microstory closest to the bone. She gives a talk at a mid-tier conference, carefully walking through a biometric model where the matter-light cone opens relative to gravities. People nod at the slide showing how the horizon scale grows. Eyebrows lift at the slide proving local tests stay intact because the two cones coincide today. In the hallway, one faculty member says, "Clever." Another says, "You're unemployable if you keep this up." She laughs like it's a joke. It is. Evidence standards were the battlefield. The inflation camp could point to the acoustic peaks in the CMB, beautiful, precise, and in tight harmony with a story of nearly scale-invariant fluctuations. VSL had to show it could generate the same spectrum without the inflaton, and it had to do it without fine-tuning CT into an ad hoc soundtrack. Produce perturbations with the right tilt. Keep them Gaussian. Suppress or predict a tensor signal. This is where reviewers sharpen pencils. Your C variation looks like a unit redefinition. Show us an invariant prediction. Name an observation that would kill it. They weren't wrong to demand it. Meanwhile, the culture did its quiet work. Grant panels asked for safe deliverables. Senior mentors redirected students to adjacent topics. Papers languished in review for months while softer speculation sailed through. That asymmetry cut both ways. Not every contrarian is a prophet. Plenty of fringe ideas die because the world refuses them. Gatekeeping filters noise. But anomalies get buried the same way, slowly, politely, by starving them of oxygen. The heretics adapted. They framed VSL not as a demolition of relativity, but as a contextual shift. Keep local invariance, the speed of light the same for any local free-falling observer, yet allow the limiting speed to run with a cosmological background field. In that phrasing, you're not breaking labs. You're asking whether the early universe set a different stage on which the same local play unfolded. It's a thin line, but it kept the conversation technical and moved it away from caricature. What mattered in the end was whether the sky would entertain the idea. Could a variable C recast the sound horizon so the Hubble tension relaxed, without punching new holes in structure growth or nucleosynthesis? Could quasar spectra, atomic clocks, and gamma ray burst timing draw a fence that a plausible CT could still fit? Theory is cheap. Data cashes checks. The VSL pioneers knew that. They'd written their names on the line anyway. Inflation's elegance still ruled the decade, but the papers existed. They sparked seminars, hallway whispers, and a handful of stubborn careers. The rough berth was the price of asking a forbidden question in a field that prides itself on asking forbidden questions. And the only judge that mattered, the sky, was about to answer in a language both camps claimed to speak. Clues in the early light, CMB, bow, and sound speeds. While the debates raged in offices, the sky had been holding receipts for 13.8 billion years. The cosmic microwave background isn't just a glow, it's a fossilized pressure map. In that hot plasma, photons and baryons behaved like a drumhead. Gravity pulled, radiation pushed back, and waves rang out. When the universe cooled enough for light to free itself, those ripples froze. The frozen pattern is what we call the acoustic peaks, and their spacing is our early universe ruler. Here's the crucial link. That ruler, the sound horizon, depends on two speeds working together: how fast the universe expands and how fast signals travel in the plasma. One of those is the Hubble rate. The other is the sound speed, which itself rides on the physics of light and matter tightly coupled. If anything in that coupling ran different back then, if the effective speed limit setting those interactions was higher, then the ruler etched into the sky is a different size than we think. Now jump to the late-time universe. Baryon acoustic oscillations are the fossil echo of those same waves, imprinted in the distribution of galaxies. They give us a second way to read the ruler across billions of light years. You measure a preferred separation in galaxy pairs, the subtle bump in the correlation function, and translate it through a model into distances. The magic is that bow is a standard ruler, not a candle. It doesn't care about how bright something is, it cares about geometry. Set the two side by side. If the early ruler is smaller because C ran hotter in that plasma epoch, then fitting the CMB with a fixed physics model will make you infer a lower expansion today. Meanwhile, Bow, tied to that same ruler but blended with lower redshift distance information, will strain to stay consistent. The tension we saw in the opening chapter becomes a question about the ruler's birth conditions, not just about late-time candles. Here's a micro story from where that plays out in real time. A pipeline engineer sits in front of a parameter estimation dashboard, a CT branch quietly merged off to the side. She toggles it on, letting an early time rescaling propagate through the integrals that set the sound horizon. The best fit Hubble parameter climbs a bit. The baryon density breathes. Neutrino parameters shuffle to keep the first few peaks stable. She doesn't declare victory, she screens for degeneracies. But the feeling is unmistakable. The data isn't hostile to the idea that the ruler didn't have to be born at the exact size we've assumed. Of course, there's a catch. The plasma sound speed in textbook cosmology comes from photon pressure and baryon inertia, not from C directly. It's C divided by the square root of 3, modified by the baryon loading. Varying the limiting speed could mimic a change in that pressure-inertia balance, but you can't cheat all the constraints. Big Bang nuclear synthesis locks down the density of baryons by how much helium and deuterium we see. Slide things too far and you'll break those abundances. Any viable CT has to sneak through a narrow alley, early enough to reshape the horizon, brief enough to leave nucleosynthesis intact, and modest enough to keep peak ratios in the CMB where Planck saw them. Meanwhile, Bow isn't perfectly quiet either. Galaxy surveys like BOSS and DESI map the standard ruler at multiple redshifts. They see a pattern consistent with the early universe imprint, but with small tensions when combined with supernova distances. Those mismatches echo the CMB late universe mismatch. A VSL scenario that reduces the sound horizon would push Bow inferred H upward when analyzed self-consistently. That's promising, but it forces you to revisit every rung in the chain: redshift space distortions, nonlinear corrections, reconstruction techniques. You can't move one brick and ignore the wall. Another thread complicates the picture. Polarization in the CMB, especially the TE and EE spectra, is sensitive to the same physics. Change the horizon scale and you shift not just where peaks land, but how their heights interlock. The data has teeth. If an early C was larger, the acoustic pattern shifts in a coordinated way. That's a blessing and a curse. It gives you a signature to search for, and it leaves you with fewer places to hide if the pattern doesn't match. While that was happening in software, a quiet argument ran in an office about what varying C really means for the CMB. One person said, "You're just renaming the sound speed." The other pointed at the equations. The Thomson scattering rate, the tight coupling approximation, the horizon scale, all inherit C in different places. It isn't just semantics. If the limiting speed was different, you've rescaled causal contact itself, not only the plasma's elasticity. That distinction matters when you ask whether distant patches could synchronize before recombination. Immediate consequences if C ran hot early. The Hubble tension relaxes because the projected ruler shrinks. The inferred H from the CMB rises without touching late-time data. Ripple effects. You'd expect subtle shifts in bow distances, a rebalancing of baryon density and spectral tilt to keep the peak pattern intact, and constraints from lensing of the CMB that push back if structure growth goes off script. It's a tight dance. And here's the pivot. Even if the early light allows a higher C, that doesn't crown VSL. Other models, early dark energy, extra-relativistic species, can trace similar paths through parameter space. Each changes the sound horizon in its own way. The job now is to find where those paths diverge. That's why we need more than a better fit. We need a risky prediction that lands in polarization, in bow at specific redshifts, or in the crosstalk with lensing. Meanwhile, light isn't the only messenger from the early universe. Another, quieter voice carries information about how the plasma behaved and what could free stream through it. Neutrinos. They whisper constraints that can undo clever tricks, and they're about to enter the story. Neutrino footprints and the speed limits of the young cosmos. While the acoustic peak sketched a ruler, another actor set the tempo, free-streaming neutrinos. In the early plasma, anything that could move without scattering acted like a pressureless wind, tugging at the waves and shifting their phases. Change that wind and the drumbeat of the CMB changes. That's why neutrinos aren't a footnote. They're a break and a metronome. If you want to argue the early speed limit was different, you have to account for how those ghostly particles shaped the same pattern you're trying to reinterpret. Here's the stakes in plain terms. Add effective relativistic species, what cosmologists call NEF, and the early universe expands faster. That shrinks the sound horizon just like a hot or sea would. The first peak shifts, the relative heights breathe, and the inferred Hubble rate creeps up when you fit the CMB. That's good for easing the tension, but it means VSL and extra radiation can masquerade as each other. If one grows, the other can hide. Degeneracy is not your friend when you're chasing a risky claim. A hallway microstory captured the pushback. A reviewer's note landed like a hammer. Your C variation is just NEF in disguise, prove me wrong. The team stared at the line. One person said, they're right to ask. Another pulled up the equations. NEF changes the expansion rate and the free streaming anisotropic stress. A varying C threads through propagation itself, through the Thomson visibility, through diffusion length, through the causal horizon. The signatures overlap, but they aren't identical. The problem is extracting the difference with real, noisy data. Action lived in cross-checks. You don't just fit temperature, you bring polarization, especially the TE cross-correlation, because free-streaming species leave a phase shift in the peaks that a naive rescaling of C doesn't fully copy. You look at damping tails, the small-scale power suppressed by diffusion, because altering the limiting speed adjusts the photon mean free path in a way extra neutrinos don't exactly mimic. You lean on CMB lensing, which tracks how structures deflected those photons later on. Models that speed the early universe often suppress later growth. The goal is a fingerprint, not a face swap. Complications pile up. Early dark energy can also shrink the sound horizon by briefly injecting a stiff component that dilutes away before recombination. Distance ladder systematics can fake a high H if Cepheid calibrations run hot or supernova standardization misses a population drift. Dust and selection effects sneak into photometry. At every turn, someone can say, it's not C, it's your ladder. The only way through is to build tests that don't share the same confusions. That's where neutrinos help and hurt. They're clean in theory, standard model relics with a predicted background, but messy in practice because their effect is entangled with anything that changes early expansion. A person in the group wrote a margin note that changed their approach. Find a phase. Free-streaming neutrinos shift the acoustic oscillation phase by a calculable amount. Measure that shift in TE and EE precisely, and you bound NEF tightly. If NEF sits near the standard model value, there's less room for extra radiation to play the role of a shrinking horizon. Then any remaining push to higher H in the CMB fit has to come from a different lever, maybe the lever VSL pulls. That's not a proof, it's a narrowing of exits. Meanwhile, independent messengers kept circling. Big Bang nucleosynthesis ties helium and deuterium yields to the expansion rate around 1 second after the Big Bang. Extra radiation at that epoch leaves fingerprints in the abundances. If BBN data lines up with NEF near 3, you can't hide a big early expansion boost there. A VSL episode would need to be timed so it reshapes recombination scale horizons without ruining the nuclear ledger. Early, brief, and controlled. The parameter space gets smaller, but that's where a real theory earns respect. There's a human moment buried in the math. A postdoc, knees tucked into a chair, reruns a chain with a prior that pins NEF tightly to the BBN preferred value. The best fit H from the CMB comes up a notch when the CT parameter is allowed to move, even with NEF locked. She doesn't cheer. She prints the posterior plots, circles the degeneracy directions, and writes phase test next at the top. The email to the group is 3 sentences long and ends with, "Reviewer 2 will ask about damping scale. Let's be ready." Impact. Multiple models can mask the same anomaly, which means any VSL claim faces a higher bar. You're not just competing with one neat theory. You're threading a needle through a web of partially degenerate effects. NEF, early dark energy, latter systematics, dust. The payoff is that the web is finite. TEEE phase, damping tails, lensing amplitude, BBN abundances, and eventually laboratory neutrino mass measurements all cross-reference the story. If a variable C played a role, it has to show up where those strands intersect, not just where it's convenient. Before leaving the neutrino corridor, a softer whisper enters, the fine structure constant. If alpha drifted across the sky in time, atomic fingerprints in quasar spectra would notice. Those traces don't tell you C alone moved, alpha blends E, H stroke, and C, but they expand the map of what constant means. The neutrino tests fence the early universe. Alpha's breadcrumbs lead out into deep time, along sightlines that cross billions of light years. And they're next. The fine structure breadcrumbs, quasar spectra and alpha,